Right, we're now going to move on to a practical example, and I'm pleased to be able to introduce to you Peter Robinson, who's a principal engineer working for Flint & Neal in London. He's worked on a number of bridge projects, including a design check on the Paduma Bridge in Bangladesh and an assessment of the QE2 bridge in the UK. His presentation today concerns design and upgrade work for the Westgate Bridge in Melbourne, Australia. Peter.
Thank you very much, Terry. I have to admit, watching Steve use Luces was very therapeutic. I'm going to talk to you today about the work we've been involved in to strengthen the Westgate Bridge in Australia. I'll try and give you an general overview of the project, and highlight where we've used Luces along the way, and finish up with some nice pictures of the strengthening. The project was finally completed last year, and the design and construction took place over about 4 years. A brief introduction to the bridge. As I say, it's situated in Melbourne, Australia, and it's a cable stay bridge with a main span of 336 metres. The overall length of the steel bridge is 848 metres, and either side you can see there's some concrete approach viaducts. Flint & Neal were only involved in the strengthening of the steel section, so that's what I'll be talking about. The bridge has a very interesting history, I think mainly due to the collapse in 1970 during construction. So it wasn't finally opened until 1979, I think, following major redesign and years of troubles with the unions. But that's made it a very interesting project to work on. The deck arrangement, previously it was carrying 4 lanes of traffic in either direction. It provides the transport link to the western suburbs of Melbourne, which you can see in the distance, and the bridge carries 160,000 vehicles on average per day. So the problem was that the rest of the freeway had already been upgraded to 5 lanes, so the bridge was a bottleneck and providing a lot of angst to the commuters in Melbourne. It's worth looking at this shot, shows quite well how wide the bridge deck is, and that all the cables are along the centre line of the bridge. And you can see where they disappear into the deck. They're underneath that are some quite complex cable anchorages, which we'll come to later. Inside the box, it's a continuous steel box girder of 4 metres deep. The overall width, including the cantilever sections, is 37 metres, and inside it's divided into 3 boxes, which you can see at the bottom, with 4 longitudinal webs and plated diaphragms every 16 metres. All the plates are heavily stiffened, and the majority of the stiffeners are the old bulb flat types, but the stiffening is a real mess, because there's so many other stiffeners have been added before and after the collapse as efforts in strengthening. The overall driver for the project was a contract that had been signed by the state to provide 10 lanes across the bridge. And this was as part of an agreement with the road operators on the other parts of the freeway that had already been upgraded. Looking at the strengthening solution that we adopted, the final concept was simply to prop the cantilevers and turn the existing hard shoulder into an additional running lane. Other options were considered that involved widening the carriageway slightly, but studies had shown that it is safe to reduce lane widths to 3.2 metres in this case, without over short distances, without adversely affecting the road safety. So that proved to be the cheapest option, as well as the local strengthening of the by propping the cantilevers. There was an awful lot of internal strengthening to cope with the global loads of 10 lanes, and also the weight of strengthening. So we've got lots of stiffness strengthening, splice strengthening, and the diaphragms and towers, as we'll see. The loose-ash modelling, we decided fairly early on to use a shell model of the bridge, and this was done with the rigidity type elements in loose-ash, which are ideal for stiffened plates. Shell models aren't, I don't think, traditional for big cable-stayed bridges like this, because you end up with such a large model, but it's quite possible to run them on desktop computers, so worth doing in this case because there's a number of advantages. Those are mainly that it deals with all the distortion and shear lag implicitly in the model without having to go into any complex calculations. Trying to work out distortion for a structure with 4 webs, I think, especially around the anchorages, would have been extremely difficult. The only downside of having a shell model rather than a beam is the processing of the results. You end up with a lot of individual element results rather than convenient forces and moments in a beam. The permanent load case, I think it's interesting to see how much the bridge has deflected over the years due to the sagging of the cables. And we did an envelope of that you can see there on the 2007, the more recent survey, up to 1/3 of a metre deflection. And that, although that stretching the cables doesn't change the cable tensions a huge amount, it did add considerably to the stresses in the deck, the sagging at the midspan and the hogging over the towers. And we did an envelope of both those cases in case they want to come back and retension the cables in the future. The traffic loading, the traffic load definition is specific to Westgate Bridge because it was derived from the weigh and motion data on the bridge. It was generated by creating an awful lot of load cases using autoloader. I think if we did that again, we would probably run unit loads across the bridge and either integrate the influence outside of loose-ash or the new loose-ash brute force influence line loader, I think, does similar things. Moving on to the construction loads, because of the history of the bridge, the handling of the construction loads was a particularly sensitive issue, and this was made all the more difficult by the fact that the bridge was overstressed under the 8-lane loads, partly because the cables had sagged, and also the first thing the contractors wanted to do was put some temporary concrete safety barriers along the whole length of it. So we decided to limit the loads during construction to the existing 8-lane loading, and this was achieved with nighttime closures, which sounds counterintuitive, but the theory is that at night the ratio of lorries and heavy vehicles is a lot greater, so the theoretical maximum load is much larger. The gantry movements were all modelled to determine at what point the critical pieces of internal strengthening had to be completed. So there were quite a few hold points where the gantries would have to wait if they got there, if the internal strengthening hadn't been done. But that all proceeded very well. Some of the detailed models, because we had a shell model of the bridge, it was very easy to create detailed models by just adding or refining the mesh in the area of interest. So this shows the anchorage where the cables disappear into the deck, and it's quite a complicated area with lots of diaphragms. This is a close-up of the section in the wall there, and that model is all attached to a global model of the rest of the bridge, so there's no need to worry about boundary conditions or applying loads to local models or anything like that. And this was the big plus, and it also tells you the distribution of loads in the webs and diaphragms around. I mean, all the vertical shear is going along the outer webs and has to make its way to the centre of the bridge to get to the cable anchorage, and there's several different diaphragms that it could choose. So having information about how that load was distributed was very useful. Some pictures of the strengthening. The internal strengthening, I think it's worth pointing out that for the assessment, the actual analysis using LUSAS is only half the battle, and there's still the task of checking against all the element capacities, which for stiffened structures like this can be very complex. The codified checks we used were to BD56 and in many places the IDWR, or Interim Design and Assessment Rules. And these were the set of rules that were drawn up in the 1970s following the collapses of bridges such as Westgate, which makes them ideally suited, and they're still the most accurate tool for the job in many respects for this sort of bridge. We did use some nonlinear FE to look at local buckling of the bulb plats. The cantilever props, I think, are interesting from a construction point of view, because they were all installed, as you can see, from a platform slung underneath the cantilevers. And this platform was gradually slid along the whole length of the bridge and carried with it its own kitchen, toilet, and obligatory smoking area, which saved a huge amount of time, because the number of lunch breaks and smokies that they would have had to go back and forth along the length of the bridge. So the contractors were very good at organising that sort of thing. I put this in because it shows the pre-stressing we put on the bottom flange, and it's quite interesting. It's quite unusual to find large amounts of pre-stressing on the flanges of steel box girders, but this was needed to overcome some tensile overstresses in the flange plate, and also overstresses at the splices, which would have been very difficult to fix otherwise. The pre-stressing extent, it goes over 60 metres of flange, and obviously anchorages at both ends only, and you just have to drill a load of holes in between, so it's quite easy to install. This shows some interesting strengthening on the towers. On the right there is the view of the base of the tower just above deck level, and on the left is where it penetrates the deck, taken from inside the box. The bolting was done using close tolerance bolts, because to avoid weakening the existing material. If you put bolts using clearance holes, then the steel would have had to yield and compress before the section was re-established, if that makes sense. A lot of work was done early on for improving the access, and this helps a huge amount for the works that were taking place later. So the openings in the webs and, or where possible, and the diaphragms were enlarged. The final slide. It's lunchtime. I won't go on about the awards, but I do have a couple of conclusions. I think with modelling, I should apologise. The model does look quite like the bridge, and broke Steve's rule there. And it's also completely different from the model the designers would have used, which is, if you're doing this assessment, generally it's a lot easier and you find fewer problems if you have start with a model that's similar to the original designers. Otherwise you just find problems in places where they didn't. So we broke that rule as well, but the benefits of not having to do all the local models and all that, I think, more than outweighed any problems we found. It's also worth bearing in mind that your model is compatible with the whoever happens to be doing the category 3 check, or that they're using a similar one, because disagreement there isn't helpful. And the only other conclusion is something similar regarding the assessment codes. It's always it's essential to bear in mind what codes the bridge was designed to. And in this case we had the old IDWR that was written at the time, which was definitely the one to use. Thank you.